Alright, this is lesson 5.5, solving systems of equations algebraically, something that I'm calling the interactive edition. So what I'm going to do in this lesson is I'm going to be asking you to click on some different things and just basically have some fun, play around with the material and get interactive. This lesson builds on a concept that we first covered in grade 10. And in grade 10, it was the last unit that you likely completed. It was on systems of equations, but it was on systems of linear equations. So we had two lines like so. And with these lines, what we would try to figure out is how many solutions that they had. And so if you recall, if the lines had different slopes like so, they had one solution. So we have one solution right in the middle. If we had two lines that had the same slopes like this and were parallel with different y-intercepts, they had no solutions. If we had two lines that had the same slopes and the same y-intercepts, they had an infinite amount of solutions. Now in this unit we're going to kick it up a notch. As we've been dealing with before, we've been looking at quadratics. So we're going to have a couple different types of systems. The first type of system we have is going to be one that I like to call a quadratic linear system like this. So we're going to have a quadratic and a line, and we're going to try to figure out how many different solutions it has. In addition, we'll look at a quadratic system like so. We're going to figure out how many different solutions it has. And in addition to just figuring out how many solutions it has, we're going to learn about how we can find out what these actual solutions are, where they intersect the graph. So last year in grade 10, we looked at three different methods to find those points of intersection. We either used the substitution method, the elimination method, or we learned that we could graph. All right, so let's get started with the lesson. A solution of a linear quadratic system of equations is an ordered pair xy that satisfies both equations in the system. So what we're trying to find out here is we're trying to find what that point of intersection is. That point of intersection is going to be an ordered pair, and it satisfies both of them. So if we take a look, let's pretend like we drew this quadratic, something that looks like so. Okay, of course that's just a sketch. I want you to think about if we had a quadratic and a linear system. So if we shoot a line across this thing, so we shoot a line maybe here, or maybe we shoot it here, or we shoot it here, or we shoot it here. How many different scenarios can we have? How many different solutions can we have? So I'll help you out with the first one a little bit. If we shot a line right across at this stage right here, notice that we have one solution and two solutions. My question for you now is, can you shoot a line across and get a different amount of solutions? Could you have three solutions? Could you have four solutions? One solution, no solutions? Play around with that. All right, good job. All right, good job. You answered correctly. As we can see, if we shoot a line across our quadratic like so, we could have two solutions like so. So I'll write that in here. A linear quadratic system may have two solutions. If we have a line cross right at this stage, it can intersect once, so we can have one solution. And if we have a line going beneath the quadratic, we can have... All right, it looks like you weren't too sure about what was going on here, so let's take a look a little bit further. If we take our quadratic and put a line across it, like I had in the first example, you'll notice that it crosses at 2 points. So since it crosses at 2 points here, these are two different ordered pairs, and that represents that there would be two solutions that would satisfy this system of equations. So we would say that there is two possible solutions. Now, in addition, we could also have a line cross and give us only one solution. What would that look like? It would just touch the graph at one single point right there. And the third possibility, as you can see, is if we had a line cross somewhere down here, we could also have no solutions. All right? It's not possible to have more than two, but we can, as you see, have 1 and 0 solutions. Example 1, solve this system. If you take a look at the system we have here, we have a linear quadratic system. The equation on the bottom is a linear system, and the equation up top here is a quadratic. How we can tell that is, of course, it's raised to the power of 2. Now, there are three different ways that we can go about solving this. We could solve by graphing, but if you recall from grade 10, graphing is one of the least efficient ways because often it's quite hard to tell accurately where the two graphs intersect. And we can solve two different ways. The two other ways that we could solve is by substitution or elimination. Now at this point in the video, I'm going to give you the opportunity to try solving this on your own. I think some of you are likely capable of doing this, remembering some of the things that you learned in grade 10. So for substitution, which is how I'm going to do it, you'll notice I'm going to take one of the equations and put it into the other one. So if you want to, click on the button right here and you can fast forward to the end to see if you can do this on your own. Alright, so let's solve this system together. It's up to you how you want to go about doing this. There's a couple different ways to play it. I'll show you what I suggest. Before I start, I like to label my equations. I'm going to label the top equation as equation 1 and this bottom one as equation 2. So it'll help you understand what I'm talking about. So I'm going to take equation 2 right here. I'm going to rearrange it for one of the variables. The variable that I'm going to rearrange it for is y. So if I rearrange it for y, I'm going to move the x to the other side of the equation and have y is equal to negative x minus 3. Now the advantage of rearranging that for y is that if you notice now, both of my equations are set equal to y. So what I'm going to do is I'm going to go and take all of this information right here, and I'm going to substitute in for that y. So if we take a look now, I will have negative x minus 3 is equal to 1/3 x squared minus 3. And now it's just a matter of us using our algebra skills. We're going to move everything to one side of the equation, and then we're going to solve by either factoring or perhaps using the quadratic formula. So at this stage, I would notice that if I add 3 to both sides of the equation, right here and right here, that these will both cancel. And so I'm left with negative x is equal to 1/3 x squared. Now from there, I notice that I have an x squared and an x left in the equation. I'm going to move everything to one side of the equation. I have 0 now is equal to 1/3 x squared plus x. From there, I notice that I can factor an x from both sides of the equation. And so I'm left with, in the brackets, 1/3 x plus 1. Now these represent my two factors, this being my first factor and this being my second one. I'm going to take each one of these factors now and set them equal to 0. The first one's going to give me x equals 0, so that's one of my solutions. And the second one, a little bit more complicated right here, I'm going to take 1/3 x plus 1 and set it equal to 0. And now I'm going to have to solve a little bit. So in order to do this, I'm going to move the 1 to the other side of the equation. I have 1/3 x is equal to negative 1. And then in order to get rid of the 1/3, what I need to do is I need to do one of two things. I can divide both sides of the equation by 1/3, or I can multiply both sides of the equations by 3. I'm going to elect for the second opportunity there. So if I multiply this side by 3, what I've done is 3 1/3, if you recall, 3 1/3 is just 3 over 3, or just 1. So I've gotten rid of this. But whatever you do to one side, you have to do to the other. And so, as we can see, I found two solutions right here as x equals 0 and x equals negative 3. But remember, the scenario that we have here is we have a quadratic and a linear function. So I'm not sure that the graph looks exactly like this, but let's pretend like it does. All right? I have two different solutions right here. How I can tell that I have two different solutions is I got two different x values like so. And so now what I'm going to do is I need to find out what the corresponding y values are. So in order to find out those corresponding y values, I'm going to take these x values that I found, I'm going to put it back into one of my original equations. The equation that I'm going to use, I'm going to use equation 2. So I'm going to write ourselves a little bit of a statement here. I'm going to say, let's sub x equals 0 into equation 2. So now it's obvious to everybody about what you're doing. So if I put 0 in there, I would have 0 substitute with brackets plus y is equal to negative 3. When we rearranged for this, we found out that y is equal to negative 3. Now, I don't want you writing your solution like that because remember, our solution is actually an ordered pair. So your final solution right here for this first ordered pair would be the ordered pair 0, negative 3. So we've dealt with one of our solutions. Solution number 2. Well, I'm going to do the exact same thing here, only I'm going to substitute in this negative 3. So I'm going to say sub x equals negative 3 into equation 2. Now, could I have substituted into equation 1? Absolutely. The reason I'm using equation 2 is, frankly, I just think it's easier to deal with. So, substituting it in, we would have negative 3, substituting with brackets, of course, plus y is equal to negative 3. If you add 3 to both sides of the equation to isolate y, we get y is equal to 0. And so notice that the second ordered pair that we get is the ordered pair negative 3, 0. So that tells me that I have two solutions, and one is at 0, negative 3, the other one is at negative 3, 0. Now the nice thing about these solutions, and really this entire section, is if you are ever in doubt, you want to make sure that you have the right answers, what I would suggest you doing is take those answers and sub them back into the original equations like this, and if the left-hand side equals the right-hand side, you know you're good to go. The beauty of this is that at the end of your test, especially with this section, you should be able to mark it for yourself, and you can tell yourself if you got it right or wrong. Alright, so just like with a linear quadratic system, the solution of a quadratic system of equations is an ordered pair, x, y, no different, that satisfies both equations in the system. So So what I'd like you to do now is I'm going to draw a quadratic on here, just like the last one I did. Okay, it's pretty ugly as per normal. I want you to think about what are the different scenarios that we could do if we had two quadratics. So for instance, I'll give you the first one. If we have a quadratic like so, and I put another quadratic in here, you'll notice that we have two solutions. My question for you once again is it possible for you to have more or less than two solutions? Give it a try. Alright, good job. As you can see, there are a number of different possibilities. We can have two solutions like we have here. We could have one solution if the graphs just kissed off of one another, like so. We could have no solutions if the graph was like so. Or if the graph was basically right on top of one another, which is tough to draw, but if we had that scenario, we could have an infinite amount of solutions. So depending on the case, we could have 0, 1, 2, or an infinite amount of solutions. Alright, perhaps you need a little bit of help with this one. If we take a look, the first example I gave, if we have a quadratic like so, it's quite easy to see that there's a possibility for us to at least get two solutions. Now, what would happen if we moved that quadratic down a little bit? Perhaps we moved it down to this stage right here. Well, if the graphs just barely touched, and I like to say they kissed off of each other right there, we have the possibility to have one solution. Now, what would happen if the graphs didn't touch at all? Well, if that's the case, if we had something like that, notice that we wouldn't have any solutions. The graphs don't intersect at all. So far we had two solutions, one solution, and no solutions. Is there anything else? Well, the last one, and you might remember this back from grade 10, was, remember when we have two linear functions? If the lines were right on top of one another, so let's say we had the blue line and the red line, how many solutions that made? That made infinite amount. So we can have the same thing here. If I put a line on top of this one, let's make it blue, like so. Let's pretend like those are the exact same quadratics. We would have an infinite amount of solutions. So depending on the scenario, we could have 0 solutions, 1 solution, 2 solutions, or as we just looked at, an infinite amount of solutions. Alright, let's dive into example 2. Solve this system. Now notice that this system is an example of a quadratic system. So again, we could have 0, 1, 2, or an infinite amount of solutions. I know it's a quadratic system because I see this is raised to the power of 2 right here, and this is raised to the power of 2 right here. As with the previous example, I'm going to encourage you to perhaps pause the video here and try the example on your own, and then fast forward it using the button on the side. Alright, let's try this example together. So just like with the last example, I'm going to label these equations as equation 1 and equation 2. Notice that we have two different quadratic equations. One's in general form and the other's in standard form. I'm going to take the one that's in standard form and convert it to general form. So we're dealing with basically the same type of terms. So in order to do that, let's deal with this guy. I'm going to go y is equal to, and I'm going to use the distributive property with the x plus 2 and the x plus 2. Like so. Simplifying here, or foiling as some of us call it, x times x is x squared, x times 2 is 2x, another 2x makes 4x, and 2 and 2 makes plus 4, minus 1. Gathering my like terms, I get x squared plus 4x plus 3. So the nice thing about these two equations is notice once again, this equation is isolated for y, and this equation is isolated for y. So what I can do is I can take all this jazz right here, and I'm going to substitute it into that equation. So once I do that, now I have x squared plus 4x plus 3 is equal to x squared minus 4x minus 5. Now what you might recall is whenever you have the exact same thing on either side of the equation with the same positivity or negativity, those are going to cancel out. If I subtract x squared from both sides, those are gone. So now what I'm looking at is I have basically two linear functions on either side here. So what I'm going to do is I'm going to try to isolate my variables together. So I'm going to add 4x to both sides. The reason I decided to get rid of this one from that side of the equation is that's going to make a positive amount of x's over here, which I like to have. So now I have 8x plus 3 is equal to negative 5. And now to isolate my x's, I have to get rid of that 3, so I will subtract 3 from both sides. Subtracting 3 from both sides gives us 8x is equal to negative 8. Now from there I'll divide both sides by 8 and 8, and this gives me x is equal to negative 1. Well, this is kind of interesting. Because we only have one solution for x, there's only going to be one solution for y right here, I think. Let's take a look. If we substitute this negative 1 into this equation like so, it doesn't matter which equation I'm going to use. I'm going to use just the second equation like that. I will sub, so I'll make a little statement here to let everyone know, sub x equals -1 into equation 2. Of course, like I said, you could have used equation 1 if that makes you feel warm and happy inside. We would now have y is equal to -1 all squared minus 4 times -1 minus 5. -1 squared is 1. -4 times -1 is +4. And if we subtract 5 from here, notice that we get 0. So we have the ordered pair -1 and 0. So in this scenario, what type of quadratics do we have? We have those type of quadratics that were kissing off of one another. So we had the quadratic like so, and the quadratic like so, where this point right here was the ordered pair -1, 0. And just so you can see, so I know that I had this question right, if we quickly go and substitute into equation 1, just because we want to be sure, let's take a look. If I was to put a -1 in here and add 2 to it, that would give me 1. 1 squared is still 1, and 1 minus 1 is 0, which was what we were expecting to get. All right? So that's example 2. All right, perhaps we could use an additional example. Notice that this is a linear quadratic system. So to solve this, what I normally like to do, and you don't always have to do this, but I like to get my y's isolated. So I'm going to change this equation to be y is equal to x plus 4. And so what that means now is that everywhere that I see a y in the other equation, I can substitute this in. So I have x plus 4, which I have taken and put it in for that y, is equal to x squared plus x. Now again, noticing that we have an x on both sides of the equation, those will cancel. And I'm sitting now with x squared equals 4. Now this is kind of an interesting situation right here. There's two different ways you can go about solving this. The first way is that you can right away, to isolate x, take the square root of both sides. And so we can get x is equal to, remember we get plus or minus 2. That's something students often forget. Or let's say we were looking for a different option. If we were sitting right here with the 4 is equal to x squared, you could have moved the 4 to the other side of the equation. So we'd have 0 is equal to x squared minus 4. And notice that this is a difference of squares. We would get x minus 2 and x plus 2. And so this gives me two solutions. X is equal to plus or minus 2. So now that we know what our x coordinates are, we need to find the corresponding y coordinates. So I'll tell the viewer what we're doing. So we say sub x equals, let's do the positive 2 first, subs x equals 2 into equation. Oh, I haven't labeled them. Let's do that. 1 and 2. Which equation do you think is easier to deal with? I'm thinking it probably doesn't really make any difference. I'll put it into equation 2. So to do that, I would now have y is equal to 2 squared plus 2. And so when we do this, we have 2 squared is 4, plus 2 is 6. And so we found out that the ordered pair right there is the ordered pair 2, 6. Okay? And if we want to make sure that works, if you take a look closely, if we put that back into the first equation, I would have put in the y coordinate. I have 6 minus 4 equals 2. We know that that one's good to go. So this, of course, is one of my solutions. Now we've got to go find my other solution. So I'll write myself a little bit of a statement here. Let's get a little bit more real estate. I will say sub x equals, this time I have to do the other value, the negative 2, into equation 2 as well. And so we'll have y is equal to negative 2 all squared plus negative 2. Negative 2 squared is 4, and 4 plus negative 2 is just minus 2. This gives me 2. And so this tells me that we have the ordered pair negative 2, 2. Okay? And if we want to make sure that this one is correcto, which we think it probably will be, let's just make sure, and we'll put it back into the original equation. Where is it? Right here. So if I was to put 2 in, and I subtracted 4, I would get negative 2. So that's how I know that that one's right. So in the highlighted yellow right here, those would be my two solutions. All right, let's try an additional example, a quadratic system. How can we recognize it's a quadratic? Well, if we take a look, we have this raised to the power of 2 and this raised to the power of 2. So to solve this, it's up to you. There's a couple of different plays, but what I notice is that both equations are set equal to y. So what I can do is I can take this whole equation, since it's set equal to y, and substitute it into this y. That would give me 2x squared plus 10x plus 12 is equal to negative x plus 3 all squared. Now, if I have this negative x plus 3 all squared, what I'm going to do is I'm going to change it from standard form to general form. So I will go and use the distributive property here with the x plus 3 and the x plus 3. And what does this give me? It gives me negative. I'm going to leave the negative outside, kicking it for a second. Distribute everything here, or use the FOIL method. X times x is x squared. 3 times x, and then 3 times x again gives me 6x. And then 3 and 3 is 9. Finally, distributing in the negative is negative x squared minus 6x minus 9. Now, setting this equal to the other side right here, I'm going to now go, just like I've been doing all unit long, and bring everything to one side of the equation. So bringing everything to one side of the equation, I'm suggesting you bring everything to the left-hand side to leave your x squareds positive. So adding an x squared to both sides gives me 3x squared. Adding 6x gives me 16x. And adding the 9 to get rid of the negative 9 gives me positive 21, is all equal to 0. Now at this stage, my suggestion would be try to use the factoring methods that we know of, if at all possible. So what we normally do if the leading coefficient is something other than a 1 is we use what I call the AC method. So let's take a look at that. And of course, just so you know, if the AC method didn't work, or you're not comfortable using the AC method all the time, you could use the quadratic formula. So in this case, let's make a little note over here. We have A times C is 3 times 21, and in this case we get 63. Now, do we know of any numbers that multiply to give me 63 that have a sum of that middle one? I think we do. 9 times 7. Let's use those. So, using the AC method, we have 3x squared, and it's up to you how you want to distribute this 16x. I'm going to write it as 9x plus 7x. So, of course, those add to give you 16, multiply to give you 63, plus 21 equals 0. What can we factor in the first two terms? You can factor out a 3x, which will give you x plus 3, and then I always take whatever that bracket is and I write it over here. What would I have to factor out of there to give me an x plus 3? Notice that we have to get rid of the 7 to get to the x, so I'll take out a positive 7, like so, and we see that one of my factors is 3x plus 7, like so, and the other one has x plus 3. Now if we set each of these equal to 0, this first one is going to give me 3x plus 7 equals 0, or 3x equals negative 7, and x is equal to negative 7 thirds. So I'll just circle that one for now. And then the other one over here is going to give me x plus 3 equals 0, or x equals negative 3. Okay? But we're not done. All right, we got our work cut out for us here. We have one that's going to be fairly easy to deal with, and that's the negative 3. I'm going to deal with that one first. So if we deal with this negative 3, I'm going to go and take that and put it into one of the first equations. So I'll leave it right there so we can see. I'll make ourselves a little note here. All right. So let's sub x equals negative 3 into, and we've got to figure out which equation we want to use. I'm going to use equation, we'll label these as 1 and 2. I'm going to use equation 2. So this gives me y is equal to negative, and I substitute in the negative 3, always use brackets, plus 3, all squared. Well, this works out quite nicely. Negative 3 plus 3 is just 0. 0 squared is 0, and 0 times negative, that's technically a negative 1, is 0. So we have a solution as 0 and so we have a solution as negative 3 and 0, like so. Let's take a look at the other one. So again, I'm going to go and write myself a little statement. I'm going to sub, in this case it's going to be the x equals negative 7 thirds into equation, doesn't really matter, I'll use 2. And so I get y is equal to negative, brackets, negative 7 over 3 plus 3 all squared. Now, a little bit more complicated, I get that. So what we're going to have to do is I'm going to simplify inside my brackets right here. In order to do that, I'm going to get myself a common denominator. So I'm going to put everything over 3. Now the negative 7 is already over 3, but the 3 technically over here is out of 1. So I multiply the numerator and the denominator by 3. So that gives me 9 over 3, all squared. If we simplify, negative 7 plus 9 gives me 2 thirds, which is squared, and there's a negative. So now I'll go and square everything. That gives me 2 squared is 4, 3 squared is 9, like so, and then that's all multiplied by the negative, which gives me negative 4 over 9. So my first solution, if we recall, was negative 3, 0. My second solution is going to be the ordered pair. Remember what I substituted in? I substituted in the negative 7 over 3, and what did I end up getting out? I got out negative 4 over 9. Those are my two solutions, highlighted in yellow. So, to summarize this lesson, we saw that we could have a quadratic system, a quadratic linear system. A quadratic linear system could have two solutions, one solution, or no solutions at all. A quadratic system could have two like so. When they kissed off each other, it had one. When it was down here, it had none. And when they were right on top of each other, we had an infinite amount of solutions. We also looked at how we could solve these. Now, the nice thing about solving it is we're just using our algebra skills that we should be fairly strong with. The method that I'm suggesting, I think you'll find the easiest, is solving by substitution. Although in class, and what I wouldn't mind you exploring on your own, is looking at trying to solve these using elimination. Is that even possible?